Okay, so now we're going to discover a technique called rule induction that allows us to perform proofs based on an inductive predicate. And the good news is that rule induction is really just the same as a structural induction on an inductive type, right? Because inductive predicate, inductive type are the same thing, then rule induction, structural induction are the same thing. The only difficulty is that most inductive predicates we deal with are dependent inductive types, like vector at the end of lecture 4. So that means the inductions that we do are also more complicated, just like the induction on vector. But we're in lecture 5, not in lecture 4, so it's normal that things get a little bit more difficult, where we should be able to handle it. And the good news is that Lean does everything for us, so we can often carry out proofs without even turning on our brains, for better or worse. So let's see. Let's perform a few proofs by induction. So it's the same command as before. It's called induction prime, and I recommend that you don't forget the prime because it really makes the command a bit better. And we'll start by proving that our definition of even as an inductive predicate implies the mathematician's definition, in terms of mod. So we assume that n is even, right, for some natural number n, and then we show that n mod 2 equals 0, right? And then we do the proof first by induction. We do the induction on h, right? Because what is h? H can be seen as a proof that that n is even, right? So, or a proof term. So we're going to do an analysis on that proof term and see, which of the two constructors of the proof term were used, because even had two cases, 0 case or add 2. Or we can say, well, H is an inductive predicate, and there were two introduction rules, and when we do an induction, then it's called rule induction, so it follows the rules. So it says, well, either you're in the first rule or in second rule. So you can really have this dual view in your mind, and choose whichever you prefer. You can think of it as data type, think of it as an inductive predicate, and you do rule induction. So here there are two cases, 0 and add 2. So in the 0 case, we just need to prove that 0 mod 2 equals 0. There are no variables in here, so often REFL can do it. And then you have the add 2 case, where you have k mod 2 equals 0, and you have to prove k plus 2 mod 2 equals 0. You see, we're really just following the definition of even, right? So even said that, if this is even, then that is even. And now we're trying to do the same, but with our current goal. We're trying to follow in the tracks of even. This predicate here, normally we don't need it. I mean, once we've performed an induction, on a predicate like even, usually we don't need to refer to that predicate again, but just in case we do have the information that k is even. But here we're not going to need it. I could clear it. That would be like this, clear Hong Kong. And here simple simplification does it. I could do it, slower. I do sim first, then I'm like, oh, this is just exact IH, right? But often we see where it goes. As this in German, you see where the rabbit is going. Maybe people say the same thing in Netherlands, I don't know. Hello, Germany, by the way. So here's a second example. This one is to show that any number of the form 2n plus 1 is not even. So it's a bit more rock and roll. So first we do intro h, right? Because this not is really an implication. And when the implication is at the root symbol, then we do an intro, right? And then also we have the even in hypothesis. And this is where we want to have it to be able to do an induction on it, right? So normally we do an induction on a variable like n, for example, structural induction on n. Well, it's also in the hypothesis then, but now we're doing an induction on h, which is there, right? And then, okay, we have to prove this thing, and the induction hypothesis has a for all quantifier here, Okay, why, you know, on top of my head, I actually don't know exactly why. Oh yeah, of course, it comes from here. This is this n. That's where the n comes from, the quantifier. But very often when we use a proof assistant, we don't fully understand the goal, but we trust our intuition that, okay, I've done induction, so I should have a reasonable goal and I should be able to continue. So I don't, you know, spend much time just trying to double check that everything is how it would be if I had done the computations on paper. But the guide has the details. It tells you exactly how Lean generates these, well, pretty exactly how Lean generates these goals, so that you really understand what you're looking at and why you have that. So it pays off to maybe not, you know it completely by heart for the most complicated types or anything like this, but at least have a, you know, a general idea of what a rule induction looks like and why it looks like it the way it does. Okay. And now, well, things are a bit tedious. Mathematically, we have k plus 1 equals 2 plus n, and we must find a value here. You know, what we're going to do really is take this false here and resolve it in some sense against that false. So they should cancel each other out. And then we're left with that as a goal. And we're going to have to prove this. But we know some things about the relationship between k and n. We know that k plus 1 equals 2 times n. That's the line just above. So, right. What do we have here? So I mean, what I figured out just by doing a bit of arithmetic is if we take n minus n here, so the one that is bound to be n minus 1, then you know, this here will be true under that condition, something like this, right? So now we have to prove that condition, which emerged from the induction hypothesis, which I just applied. Could at this point just remove the induction hypothesis just to clear up the state. And then what do I do? Well, here's the problems that we have a -1 on natural numbers, and that's always bad news because natural numbers cannot go into the negative. So 0 minus 1 is 0. It's not -1, so it's an exceptional case. So you want to treat the 0 case differently from the other cases. And the best way to do that is to use cases, or cases prime here. And then you have the 0 case. And then you have 0 minus 1 explicitly, and it's going to simplify to 0. And there's a tactic called linearit, which is a bit like CC, except that it knows about, I mean, its special power is to know about arithmetic operators, especially plus, minus, and also a little bit of times, so times 2, times 3, and so on, as long as it's not two variables that are multiplied. And then we do the successor. Successor has this annoying suck here. So here I'm, you know, I'm using this lemma, which I just pull out of my hat, to rewrite it into a +1. So it's quite useful lemma. You'd wish that linearit would do that automatically, but it doesn't. So we have to live with it. Have to go to war with the army we have, not the army we'd like to have, right? And that's it. That concludes the proof. So this is a tricky little proof, which is also quite instructive and also taught us a new tactic, linearit. And we'll learn more and more tactics as we go. So our language will grow. So we'll spend less and less time doing these baby steps and more time doing actual interesting theorem proving. Right. So this is an example of what linearit is able to do. So it also knows about greater than, and so if we know that I is greater than 5, then we know that 2 times I plus 3 is greater than 11. Linearit can do that, and it will just inspect the entire state, including the hypothesis. You don't. It's not like other tactics where they're completely blind and you have to tell them, oh, use this hypothesis or use that hypothesis. Another example, I'm not going to go into details here, but it's about the star operator, the reflexive closure. So here we're saying that taking the star twice is equivalent to just taking it once. And the first thing is we have an if and only if. So we end up with two sub-goals. There's one direction that is trivial, and the other direction has an induction. And the induction has three cases, right? It creates three cases, the base case, the refl case, the trans case, because that's how we've defined reflexive closure, reflexive transitive. In the base case, there's nothing to do. We just happen to have the right hypothesis. And yeah, that hypothesis comes simply from the fact that we, that we know when we perform an induction, we obtain all the information that we put in at construction time. So if I go back to the closure, whoops, it's over here. All right. So here we had to provide this to obtain that. So when we do an induction, and we're in this case, then we retrieve this information here. And in that case, we retrieve the information that A equals A, right? That these two things have to be the same. So we're going to see that as well. And in this case here, we retrieve these two pieces of information. That's what happens. So now I have to find where I was here. So in this case here, star RAB, well, that's what we get from being in the base case, right? There's one layer of stars, that's normal. We started with two layers. We're in the base case. That means we simply had one layer of star and we embedded it in two layers. So we just use that. For refl, you see it identified the two A's automatically because that's what that case looks like. And then that's easy. We can just use star.refl. And then in the last case, well, we have some induction hypotheses that help us, right? Because the transitive closure is based on two cases. Right, so, and they're induction hypotheses because if we look at the definition again, sorry, close your eyes if this is bothering you. Sorry, here. You see, this is recursive. You have star on the left-hand side here, and here on the right-hand side. These two were not recursive, but the third one is. So if we go back to star, there we go. So we have all these induction hypotheses, and that's great because here we have, you can go from A to B, you can go to from B to C, and we want to prove that we can go from A to C. So we can just apply transitivity, and then, the two goals correspond to hypothesis, right? So it's exact of a hypothesis, an induction hypothesis, exact of another one. And there, I think you really see that proof assistance can help you because you see, this is a mindless proof, really, right? So at each step, we just look, I have these assumptions and I have these rules and I plug them together, and there are not that many rules and that many options. We just, of course, we might forget one of them and be blocked, and then we ask for help and then we go further. But my point is this whole proof was fairly automatic. Whereas if we had worked on paper, this would have been quite hellish, this whole thing. And by the end, we would not be sure if we really have proved it. At least that's how I feel about most of these inductive predicate proofs on paper. And here's a little extension of that proof, which removes the two arguments and uses an equality instead. We need a property called functional extensionality to say, well, two functions, for two functions f and g to be equal, it suffices if, f of x equals g of x for all x, right? So you can prove that the functions coincide at all points, then you've won, the two functions are equal. At least that's how it is in classical mathematics. And that's also how things are in Lean, thanks to funxt, which is I think it's an axiom. It's it's a theorem here. It says, let's see. It probably follows, yeah, right, it follows from other axioms. So, okay, so we apply it. So then that gives us the first argument, which is called x. We intro it. We do the same game, play the same game again. Now we have both arguments we wanted. Now we apply a second property, which is called prop x, which transforms the equality in an if and only if. So it says to prove that two propositions are equal, it suffices to show that they're equivalent, right, which is intuitive, I guess. And then at this point, we're exactly in a state where we can apply the lemma we just proved above this one. And that's it. We've won. And this is a fun X for you. Let's see, it prints it at the bottom. Right. So for all X, these two functions are the same, then they really are the same. And prop X is just if and only if implies equality.